Hey, and welcome to the third extra video from the gatherings. We're going to look a bit on what we learned during the exercises. So first thing we learned was the part about complexification. So this is one of the things we looked at was how if we have a group that is made up of real matrices, then we can see it as also a group of complex matrices by the natural embedding of the real numbers into the complex numbers. But we can also put a group of complex matrices into a group of real matrices in the following way, which means that we can sort of shift between real and complex matrices. So if you see a statement about groups, if in GLN-R or GLN-C, like you can pretty seamlessly switch between the two. It doesn't really matter that much. Then we have a very important concept, which is complexification, which is not so difficult. It's just that it will be very important later when we come to representations of Lie algebras, because it's easier to understand representation of complex Lie algebras than it is for real Lie algebras. So if I have a real Lie algebra, then I formally can define its complexification as just taking x and then taking formally I plus y, where both of these are elements in G, and then I can extend complex multiplications of complex scalars in the following way, and I can define a Lie bracket in this way here to make sure that it's linear with respect to complex scalars. So this allows me to go from a real Lie algebra to a complex Lie algebra, and there's this universality property that says that if you have a Lie algebra homomorphism from real Lie algebra into a complex one, then you can extend this to its complexification. Then during the exercises, we saw that SU2 and SL2 were not isomorphic, but that their complexification was. And so this is an important thing to note, that some real Lie algebras are different, and then they become the same after you complexify. Then we have the following proposition, way of thinking about complexification, was that if you had a matrix Lie algebra that was a Lie algebra that consists of matrices, and it's such that whenever you had a non-zero element, if you multiply that with I, then you will get something that's outside of it. Then the complexification was just this is not just a formal sum, but it's actually just a sum of matrices x plus I, y, where x and y are in G as matrices. So that means that we can compute the following, that SU2 and SL2 have the same complexification, namely SL2C, and that GLN and the skewer joint matrices also have the same complexification, namely all complex matrices. So that's the main takeaway. So the important thing is that you know that if there is a real Lie algebra, then you can complexify it, and then that the definition of the Lie bracket extends to this complexified vector space. Then we talked about indirectly about universal cover groups. So we talked about SU2 and SO3, how they had isomorphic Lie algebras, but they were not isomorphic as Lie groups because SU2 was a sphere, a 3-sphere, so it was simply connected, whilst SU03 was not simply connected. And it had this, we saw with the bell trick, that it had this weird hole that if you went around it once, you couldn't contract your loop, but if you went around twice, then it suddenly became contracted. We have a surjective group homomorphism between SU2 and SO3, and this has kernel plus and minus I. So that corresponds to exactly this loop, which goes away when you apply it twice. And this is the case of a universal cover group because SU2 is simply connected while SO3 is not. So in general, if you have two matrix Lie groups such that H is simply connected, which have Lie algebra small h and small g, then H is said to be a universal cover group of G if there is a Lie algebra homomorphism from H to G, such that when you restrict it to the Lie algebra, it becomes an isomorphism. So essentially, you can think of this as adding some elements, some discrete element to your group, such that it no longer has any holes in it. And these groups are then unique up to isomorphism. That's what we should look for. So for nilpotent Lie groups, there's lots of a relationship from nilpotent and unipotent that you can look at. This has also been given as an exercise for earlier weeks, but one of the important things is that you can do the Baker-Campbell-Hausdorff formula explicitly because the series eventually converges, so you can define it for all elements. And also you will have that the exponential map will be surjective and invertible, so you can represent, there's a one-to-one correspondence between a simply connected nilpotent Lie group and nilpotent Lie algebra, but this is a bit too advanced for our setting. But it is also true that the other things, so the Baker-Campbell-Hausdorff is an example of a series involving the brackets or multiplication where you eventually get finite series, and this is also true for like the exponential map of the logarithm and so forth. So you can use it for all elements. Last week we talked about what a general Lie group was. So roughly speaking, since we're not doing manifolds in the course, all you need to know is that a group is like a space where we have some definition of what it means to be take derivatives. So what does it mean to be continuous? What does it mean to take derivatives? And what does it mean to be infinitely differentiable, so smooth? And in this setting, the group operation is smooth. And then very often it's also listed that the inversion is smooth, and you can include this in your definition or not. So this property you can actually, when it's defined properly, you can actually deduce that the inversion has to be smooth from the fact that the multiplication is smooth. But we won't go into that. So the point is that, okay, at least remember that the multiplication is smooth, and then the inverse has to be smooth, but this is actually a consequence of the multiplication being smooth. So some examples of Lie groups in this setting is that, of course, Rn with plus or Cn with plus are not matrix Lie groups, but are Lie groups because adding things is a smooth operation. So you can see them as matrix Lie groups, but then you have to see them as the group of matrices like this that gives you an isomorphic Lie group. But there has been times where I wanted to do the example of like Rn with plus or Cn with plus, and where I've kind of tried to avoid it because it's been annoying to write these types of matrices. So sometimes it's good to like have be able to express things a bit more compactly by not necessarily writing them as a matrix legal. Same what we saw with the exercises with the quaternions. The quaternions are what is it? Quadruple of numbers like this, where the elements I, j, and k satisfy these relationship here. You can of course also see that as a matrix group of these types of matrices, but it's of course easier to just consider these numbers here rather than this enormous matrix right here. And then finally, we talked about the fact that there are some matrix Lie groups that are not, some Lie groups that are not matrix Lie groups. So for example, we could take R2 across the circle, seen as the unit circle in the complex plane, and where we take the group operation that we add the 2 first, and then in the last one, we take C1 plus C2 plus A1 times B2. This can be considered as the quotient of a matrix Lie group. So this is it can be say H quotient out by K, where H is the upper triangular matrices with ones on the diagonal, which is called the Heisenberg group. And K is the subset of elements here, where you have 2 pi n for all n integers here. And if you quotient them out, you get this group here. And here, so this is an example of a group that's a Lie group, but you cannot write it as a matrix Lie group. Also, we talked about the universal cover group, so it also one of the results in the book is that the universal cover group of SL2R is not a matrix Lie group, but we don't include any details on that because the universal cover group of SL2R has a rather messy multiplication. But just know that that's one of the examples and one of the reasons why we want sometimes to go outside of the case of matrix Lie group, because perhaps we want something that's simply connected where we can integrate our algebra homomorphisms to Lie group homomorphism. And that means that sometimes that will be a group that cannot be written as a matrix.